Many drivers unknowingly buy vehicles powered by engines with a history of serious issues, even some that are still being built today. We're talking about the power plants that promise performance and efficiency, but delivered a host of headaches instead. Stick around as we uncover the engines that continue to be a gamble for car owners, revealing their hidden flaws and long-term costs. BMW N63 engine. Introduced in 2008 with the BMW X6 xDrive 50i, the N63 was a bold departure from its naturally aspirated predecessor, the N62. BMW was aiming to redefine V8 performance by embracing forced induction, lighter materials, and cutting-edge fuel management. The result was the world's first production turbocharged V8 to adopt a hot V layout, an engineering move that placed the turbochargers inside the V-shaped space between the cylinder banks. This revolutionary configuration drastically shortened the exhaust path, nearly eliminated turbo lag, and made for an impressively compact engine. Under the hood, the N63 is a 4.4-liter V8 with dual overhead camshafts, aluminum block and heads, and high-precision direct injection. It features dual Vanos variable valve timing, but initially skipped BMW's Valvetronic variable valve lift system, which was later added in the first major technical update. Power output has ranged from around 400 horsepower and 450 pound-feet of torque in early versions, all the way to 523 horsepower and 553 pound-feet in the latest revision. The N63 has gone through a series of major revisions. The original version, used from 2008 to 2013, quickly developed a reputation for severe reliability issues. In response, BMW introduced the N63TU in 2012, which brought internal upgrades and finally incorporated Valvetronic. Then came the N63TU2 in 2016, borrowing twin-scroll turbochargers from BMW's high-performance S63 to improve power delivery and efficiency. The latest version, the N63TU3 introduced in 2020, includes forged rods, improved cooling, and upgraded fueling systems, essentially a ground-up fix aimed at solving the engine's early flaws. Despite this evolution, traces of its troubled DNA remain. This engine powers a wide spread of BMW's luxury lineup, 5 Series, 7 Series, 8 Series, as well as the X5, X6, and X7. Tuning enthusiasts still flock to the N63, thanks to its enormous potential. A simple software tune, upgraded downpipes, and a high-performance intercooler can easily yield over 50 additional wheel horsepower. Yet while the N63 is a beast in the tuning world, its factory reliability remains a frequent point of discussion. The problems with this engine are both widespread and well-documented. Early versions are notorious for excessive oil consumption, often linked to the intense heat generated by the hot V-turbo layout. Valve stem seals degrade prematurely, leading to visible smoke from the exhaust and the need to constantly top up oil, sometimes every 1,000 miles or less. Timing chain stretch is another catastrophic issue, especially in pre-2014 models. Fuel injector failures are also common. Owners report rough idling, misfires, and black soot on the tailpipes due to unburnt fuel. Meanwhile, turbocharger failures, coolant leaks, carbon buildup from the direct injection, and even high-pressure fuel pump issues round out a daunting list of problems. There's also the mysterious rapid battery drain, often caused by parasitic electrical draws, an issue BMW tried to address by fitting larger batteries in affected vehicles. In response to the avalanche of complaints, BMW launched the N63 Customer Care Package in 2014. This massive service campaign included everything from oil services to fuel system updates and battery replacements, at no cost to owners. Thousands of vehicles were involved, covering most 5, 6, 7, and X-Series models built between 2008 and 2014. The package even included trade-in offers toward newer models due to the engine's poor reliability perception. But not all problems were solved. BMW later faced class action lawsuits regarding the N63's chronic oil consumption, specifically targeting early production years. The lawsuits accused the company of knowingly selling vehicles with defective engines, and in some cases, owners were reimbursed for repeated repair costs or offered extended warranties. While BMW denied wrongdoing, the settlements reflected the deep-rooted reliability concerns that shadowed this engine for years. Today, the most recent N63TU3 is significantly more refined, with stronger internal components, revised cooling systems, and better turbo management. Yet, even in its latest form, long-term reliability remains a question mark. If you're shopping for a BMW with this engine, aim for a 2020 or newer model. Anything earlier, especially pre-2015, is likely to bring not just performance thrills, but maintenance nightmares. Volkswagen Audi 2.0-liter TFSI EA888. Now, from Bavarian muscle, we shift to one of the most widely used turbocharged engines in Europe and North America, the Volkswagen and Audi 2.0-liter TFSI from the EA888 engine family. First introduced in 2008, this inline four-cylinder engine was born out of a need to replace the aging 2.0-liter FSI. It wasn't just about more power. The EA888 was built to be leaner, cleaner, and more compact, emphasizing thermal efficiency, fuel economy, and reduced emissions. It introduced direct fuel injection paired with a turbocharger, along with aluminum head and block construction, and variable valve timing on both intake and exhaust sides. Over time, the EA888 evolved through three major generations. The first generation, identified by codes like CDNC and CDMB, quickly drew criticism due to severe piston ring issues. These rings allowed excessive oil to seep into combustion chambers, leading to high oil consumption, engine knocking, and in many cases, premature failure. Owners often found themselves adding a quart of oil every 1,000 miles. PCV valve failures, coil pack burnouts, crankshaft position sensor faults, and even water pump leaks made Gen 1 models notoriously unreliable, especially in North America, where several class action lawsuits emerged around 2014. The second generation, known by the engine code CCZ, tried to correct the course. It featured updated piston rings to reduce oil consumption and improved reliability overall. While it was more serviceable and saw fewer catastrophic failures, it brought its own set of issues, especially with the timing chain tensioner. Chain stretch and rattling at startup became common complaints, and although these engines were marketed with lifetime chains, many failed before 80,000 miles. Because the EA888 is an interference engine, a failed chain often meant bent valves and a destroyed cylinder head, making proactive replacement not just recommended but essential. By 2013, the Gen 3 EA888 was introduced. Designated by codes like CJB and CGAV, this version brought true refinement. It was smoother, quieter, and better at managing heat and internal stress. The introduction of dual solenoid cam phasers, lighter internals, and improved software tuning helped boost both performance and longevity. Power output in Gen 3 engines ranges from just under 200 horsepower in entry-level trims to around 330 horsepower in performance variants like the Audi S3 and the Golf R. Despite the improvements, Gen 3 is not without flaws. The water pump assembly remains one of the most fragile components. Built with a composite plastic housing, it tends to warp and crack over time, leading to slow but persistent coolant leaks. This is made worse by its integration with the thermostat and temperature sensor, which complicates replacement and drives up labor costs. Alternator failures are also reported, sometimes due to bearing wear, other times electronic failure in the voltage regulator or clutch pulley. The timing chain, though improved, still stretches with age. Rattling during cold starts is often the first symptom, and ignoring it can result in catastrophic damage. Some owners also report PCV system failures, leading to vacuum leaks and smoky startups, especially when the engine has seen extended highway driving or hard acceleration. The direct injection system contributes to carbon buildup on intake valves over time. In tuning circles, the Gen 3 EA888 has earned strong respect. Tuners typically begin with an ECU remap and upgraded downpipe, often pushing power gains of 40 to 60 horsepower without touching internal components. It's not uncommon to see Stage 2 or even Stage 3 builds producing over 400 horsepower, provided cooling and fueling are upgraded accordingly. For buyers considering a used Volkswagen or Audi with the 2.0-liter TFSI, understanding the generation is critical. Gen 3 and Gen 3B engines from 2016 onward are far more robust and less prone to oil consumption and timing chain issues. Earlier units, particularly from 2008 to 2012, should be approached with caution. Ford 3.5-liter EcoBoost V6. Next, we head into the heart of Ford's powertrain revolution, the 3.5-liter EcoBoost V6. This engine debuted for the 2010 model year and was Ford's bold response to changing demands in performance and efficiency. Built on the architecture of the Duratec 35 V6, the EcoBoost was meant to replace traditional V8 by delivering similar power with fewer cylinders, better fuel economy, and lower emissions. At its core, The 3.5-liter EcoBoost is an all-aluminum, 60-degree V6, using direct fuel injection and twin turbochargers to generate a broad torque band. It features 4 valves per cylinder operated by dual overhead camshafts and uses twin independent variable cam timing, or TVCT, to optimize performance and efficiency across the rev range. Power output has ranged from 365 horsepower to over 450 in high-output variants, with torque figures climbing from 420 pound-feet to 510 pound-feet, depending on application and generation. The first generation ran from 2011 to 2016. Early models featured Hitachi direct injection, smaller turbochargers, and a long single-chain timing system. In 2013, Ford revised the turbos, upgraded the fuel system to Bosch components, and moved to an electronic blow-off valve. Despite those improvements, the first-gen EcoBoost quickly earned a reputation for several serious issues. Timing chain stretch was a frequent and expensive problem, especially in models with high mileage or poor oil change habits. The long routing and steep chain angles led to excessive wear, often causing engine noise, misfires, and check engine lights. Repairs often required engine-out service, driving costs into the thousands. The second generation arrived in 2017 and was a major mechanical overhaul. It brought in the port fuel direct injection system, solving the carbon buildup issues caused by early direct injection-only designs. New BorgWarner turbochargers with electronic wastegates replaced the older pneumatic units. The cam drive was completely re-engineered with shorter chains, one for each bank, and stronger tensioners. The cooling system also saw improvements, including piston cooling oil jets and updated intercooler plumbing. These changes significantly improved durability, but problems remained. Cam phaser failures continued to haunt owners, particularly on startup, producing a loud rattle due to failed locking mechanisms. Ford issued several technical service bulletins addressing the issue, but it wasn't enough to prevent widespread complaints. Then came the third generation in 2021, the most refined version yet. This revision introduced new cam phasers, metal timing chain guides, and revised turbo components with electronically controlled rotary wastegates. But even this updated version hasn't been free from controversy. In 2024, Ford issued a recall affecting over 8,000 units of the F-150, Expedition, and Lincoln Navigator built for model years 2024 and 2025. The issue was a misaligned engine cup plug, essentially a sealing plug that, when incorrectly installed, led to rapid oil leaks and even engine stalls. If oil leaked onto hot surfaces, the risk of fire increased. The issues list is long. Moisture would pool inside the intercooler and get sucked into the engine under hard acceleration, causing misfires and rough running, especially in humid climates. Spark plug fouling and ignition coil failures are also common. Oil pan leaks plagued 2015 to 2018 models, where Ford used a plastic oil pan that would warp and seep oil. Then there's turbocharger wear. While turbos are expected to degrade over time, EcoBoost units often suffered premature bearing wear or actuator failure, especially when owners ignored oil change intervals. Despite its issues, the 3.5-liter EcoBoost is beloved in the tuning world. It responds aggressively to software tuning, and enthusiasts often upgrade the air intake, intercooler, and exhaust system to unleash substantial power gains. With a tune and bolt-ons, it's not unusual to see output climb over 500 horsepower with factory internals. If you're shopping for a used vehicle with this engine, aim for a 2017 or newer model with clear service history. Avoid early first-gen units unless major components like the timing chain and cam phasers have already been addressed. And for owners of the latest models, keep an eye on recall notices, because even with its impressive performance, the story of the EcoBoost V6 is still being written. Nissan Variable Compression Turbo Engine. Now let's talk about an engine that was supposed to rewrite the rules, Nissan's Variable Compression Turbo Engine. When the 2.0-liter KR20DDT made its production debut in the 2019 Infiniti QX50, it was hailed as a breakthrough. Built to replace traditional fixed compression four-cylinders, it borrowed none of the mechanical simplicity of its predecessors. Instead, Nissan introduced a radically different powertrain with the promise of delivering both performance and fuel efficiency in one seamless package. But what looked great on paper has since struggled with real-world durability. This engine uses a revolutionary mechanical system to continuously vary its compression ratio from 8:1 to 14:1. That means, depending on how you drive, it can switch between a low compression ratio for high-performance turbo boost and a high compression ratio for better fuel economy. It does this using a complex multi-link setup that physically alters the piston's stroke length. This system is monitored and adjusted by an onboard computer hundreds of times per second, enabling the engine to adapt in real time to driver demand and road conditions. This wasn't just clever engineering. It was a bold, unprecedented move in mass production. The 2.0-liter KR20DDT is a turbocharged inline-4, featuring both direct and port fuel injection. It uses 4 valves per cylinder with continuously variable valve timing and an all-aluminum head and block. Turbo lag is minimized thanks to a short exhaust path and a high-efficiency electric wastegate. In lower load conditions, the engine switches to an Atkinson cycle for improved economy. Power output ranges between 248 and 268 horsepower, with torque peaking around 280 pound-feet, depending on the application. In 2022, Nissan added a second engine to the VC turbo lineup, the 1.5-liter KR15DDT 3-cylinder. It first appeared in the Nissan Rogue and incorporated further refinements such as textured valve lifters to reduce friction, high-pressure fuel injection, and stainless mirror-bore cylinder coatings for improved performance. It too features dual injection, a vacuum-cast aluminum head, and is paired with an upgraded Stronach continuously variable transmission. This 1.5-liter version even won Award's 10 Best Award in 2022 and a China Heart Award in 2021, proving the industry recognized its potential, at least early on. Tuning potential for these engines is limited, given the complexity of the variable compression system. However, ECU remapping and airflow upgrades do exist for mild performance gains. Despite the innovation, the reality has been troubling. Some owners have reported reaching high mileage without issue, but others weren't so lucky. Complaints of catastrophic failures at relatively low mileage have flooded forums and consumer complaint databases. The biggest problem with the VC turbo engine is bearing failure. Internal engine bearings, especially the main bearings and the components labeled A, C, and L links, have proven to be weak points. These parts are critical to the variable compression mechanism, and when they wear prematurely, they shed metal debris into the oil. That debris can lead to rough running, knocking, or worst of all, complete engine seizure. In some cases, this has happened suddenly while driving, causing a total loss of power and posing a serious safety hazard. Owners have also reported oil leaks and consumption problems, particularly in early Rogue models. There have been a few instances of head gasket failures and turbochargers failing either independently or in conjunction with internal engine damage. The scope of the issue came to a head in June 2025. Nissan issued a massive voluntary recall affecting nearly 444,000 vehicles in the United States, plus another 37,000 in Canada. The recall applies to both the 2.0-liter 4-cylinder and the 1.5-liter 3-cylinder VC turbo engines. The official cause: manufacturing defects in the main engine bearings and the L-link system that alters compression. Nissan admitted the flaws could lead to excessive friction and heat, resulting in catastrophic engine damage or seizure, with a very real crash risk due to sudden power loss. The recall came after a federal investigation launched in late 2023 by the National Highway Traffic Safety Administration, following multiple reports of engine seizure and power loss. By the time the recall was announced, Nissan had already been making quiet changes in its production lines, updating bearing materials, and modifying the internal geometry of the variable compression links, suggesting they were aware of the issue well before it became public knowledge. While the variable compression turbo system is a fascinating technical achievement, it's clear that the complexity introduced vulnerabilities. What Nissan hoped would define a new era of efficient turbo performance has instead become a cautionary tale. If you're looking at a used vehicle with this engine, especially a 2019 to 2022 Infiniti QX50 or a 2022 Rogue, proceed with extreme caution. Chrysler 3.6-liter Pentastar V6. The Chrysler 3.6-liter Pentastar V6 made its debut in the 2011 model year, starting with the Jeep Grand Cherokee. It wasn't just a new engine, it was a complete strategic overhaul. Chrysler needed a single, versatile V6 to replace 7 older engines. This new power plant aimed to cut complexity, improve fuel economy, and offer better NVH characteristics across the board. The result was the Pentastar, a clean-sheet design built for modern demands and wide platform flexibility. The engine is a 3.6-liter, naturally aspirated V6 with an aluminum block and cylinder heads, running a double overhead camshaft setup with 4 valves per cylinder and dual variable valve timing actuated by cam torque. It features sequential multiport fuel injection and delivers between 283 and 305 horsepower, with torque ranging from 260 to 270 pound-feet, depending on the application. Over time, the Pentastar saw major revisions. The most notable upgrade came for the 2016 model year, referred to informally as the Pentastar Upgrade, or PUG. This revision brought 2-step variable valve lift to reduce pumping losses, a cooled exhaust gas recirculation system for improved efficiency under real-world loads, and a redesigned intake manifold with longer runners that boosted low-end torque by nearly 15%. Chrysler also increased the compression ratio from 10.2 to 1 to 11.3 to 1 and introduced high-tumble intake ports, shrouded combustion chambers, and new 8-hole fuel injectors for better atomization. A separate evolution came in 2018, when select Pentastar versions were paired with a mild hybrid e-torque system in the Ram 1500 and later in the 2020 Jeep Wrangler Sahara. This 48-volt belt-driven generator replaced the alternator and added auto start-stop, torque assist, and improved drivability features. The system made the Pentastar more modern without reinventing the core engine architecture. The engine has powered a wide range of models, from the 2011 Dodge Charger and Jeep Grand Cherokee to the Chrysler Pacifica and Dodge Grand Caravan. It's been a workhorse in the Jeep Wrangler since 2012 and served as a core powertrain in the Ram 1500 starting in 2012. Despite its popularity and early accolades, the Pentastar is riddled with long-term reliability issues. One of the most notorious is the cylinder head failure, especially in early versions built before mid-2012. Cylinder number 2 would often misfire due to overheated or cracked valve seats, triggering the check engine light. Chrysler revised the head design with hardened seats and improved cooling, but not before a class action lawsuit emerged, claiming ticking sounds, loss of power, and full engine failure. Oil cooler and filter housing leaks are another widespread problem. Early designs used plastic housings that would warp or crack from repeated thermal cycling. Oil would leak into the engine valley or down the rear of the block. While aftermarket aluminum replacements exist, and Chrysler has since moved away from the plastic design, no official recall was ever issued. That's a frustrating omission for owners who've had to replace these parts multiple times. Cooling system issues are surprisingly common, too. Water pumps and radiators are known weak points, but a deeper issue lies in the engine's original sandcasting process. This can lead to chronic overheating, coolant leaks, and engine stress over time. Coolant flushes can help, but the root problem is baked into the block from day one. The timing chain system is another vulnerability. While the chain itself is durable, the tensioners and guides are prone to wear, causing startup rattle and eventual slack in the system. Some owners have also reported long cranking or hard start conditions, often tied to faulty sensors, ECM issues, or inconsistent fuel delivery. Oil consumption has been reported, particularly in early production years, and in some cases linked to faulty oil pressure switches. As a result of these widespread issues, Chrysler and Fiat Chrysler automobiles, now Stellantis, have faced multiple class action lawsuits and a slew of technical service bulletins. The lawsuits often center around premature cylinder head failure and valve train problems. Dealers were instructed to replace affected components, but many owners outside of warranty were left footing the bill. Despite thousands of complaints, Chrysler has largely avoided large-scale engine recalls for the most persistent problems. Today, the Pentastar remains in production, a testament to its design flexibility and widespread use. But with millions of units on the road and a well-documented pattern of failures, it's earned its reputation as a power plant you need to keep an eye on. If you own one or plan to buy a vehicle equipped with it, early detection and preventive maintenance could make the difference between years of trouble-free driving and a costly engine teardown. Ford 1-liter EcoBoost 3-cylinder. The Ford 1-liter EcoBoost engine, codenamed Fox, made its production debut in 2012 and quickly caught global attention. It wasn't just another downsized motor. It was Ford's answer to tightening emissions standards and rising fuel economy demands. Replacing the older, naturally aspirated Duratec engines, like 1.6-liter four-cylinder, the 1-liter EcoBoost aimed to offer equivalent power with better fuel economy and lower emissions. But what made it so revolutionary was its cocktail of cutting-edge tech, all crammed into just 3 cylinders. This tiny powerhouse features a 1.0-liter inline 3-cylinder configuration with turbocharging, direct fuel injection, and twin independent variable camshaft timing. Built around an open-deck gray cast iron block, it was engineered to warm up nearly 50% faster than aluminum alternatives, helping improve cold start efficiency. The cylinder head is cast aluminum to reduce weight, and each cylinder is equipped with 4 valves, controlled through an advanced valve train setup. One of its boldest innovations was the belt-in-oil timing system, a submerged oil-lubricated belt designed to combine the quietness and efficiency of a belt with the longevity of a chain. Supporting this core layout are features like an electronically controlled variable displacement oil pump, a split cooling system with dual thermostats for precise thermal management, and an integrated exhaust manifold cast directly into the cylinder head to reduce turbo lag and improve warm-up times. The compact low-inertia turbocharger was designed for rapid spool-up, while a novel engine balancing method, relying on a dual-mass flywheel and a vibration-dampening clutch, allowed the engine to run smoothly without the weight and friction of a traditional balance shaft. It was a highly ambitious engineering exercise that delivered on paper and in awards. The 1-liter EcoBoost won the International Engine of the Year overall title 3 years straight from 2012 to 2014, dominated its category through 2017, and earned a spot on Ward's 10 Best Engines list in both 2014 and 2015. Over its lifespan, the 1-liter EcoBoost has seen several revisions. A major upgrade came in 2018 with the addition of cylinder deactivation technology, allowing the engine to shut off one cylinder under light loads to improve fuel economy. Around the same time, Ford also began transitioning from the problematic belt-in-oil system to a more conventional timing chain for the main drive, though they retained a wet belt for the oil pump. Later versions even included mild hybrid electric support to improve efficiency under acceleration. There's also a naturally aspirated version found in some budget trims of the Fiesta. Power outputs have ranged from 99 to 138 horsepower, with torque peaking between 125 and 147 pound-feet, depending on the application. The engine has been mated to both manual and automatic transmissions across a wide variety of models, including the Ford Fiesta, Focus, EcoSport, B-Max, C-Max, Transit Courier, Tourneo Courier, and even the Mondeo in Europe. While some owners have reported reaching over 150,000 miles with no major problems, those success stories are outliers. Most headlines involving the 1-liter EcoBoost revolve around serious reliability issues. One of the most notorious problems was a flawed coolant hose design used in early models, particularly between 2012 and 2014. The rubber hose, located at the base of the engine, was prone to sudden failure under heat and pressure. When it burst, coolant drained out rapidly, often without triggering a warning light, leading to catastrophic overheating and warped cylinder heads. Thousands of engines were lost to this issue in the United Kingdom alone. Ford eventually issued an updated hose and launched a service campaign for specific VIN ranges, but many affected owners had already faced full engine failure, some without reimbursement. Then came the much-hyped belt-in-oil timing system. Marketed as a quieter, more efficient alternative to traditional chains, it instead became a time bomb. These internal belts degraded when exposed to aged or contaminated oil, shedding material that clogged oil pickups and starved engines of lubrication. In worst-case scenarios, this led to total engine failure, usually without much warning. And because the belt was submerged and buried deep inside the block, diagnosis wasn't easy or cheap. Ford initially claimed the belt would last up to 10 years or 120,000 miles, but quietly walked that back when reality struck. Other recurring problems included carbon buildup on the intake valves, a common drawback of direct injection engines that lack port injection to wash the valves clean. Over time, hardened carbon deposits would trigger misfires, rough idling, and reduced fuel economy. Despite its brilliant engineering and initial wave of awards, the 1-liter EcoBoost now stands as a cautionary tale. Its innovative features pushed boundaries, but real-world durability fell short. For many, the EcoBoost's early glory has faded into frustration, and for that reason, it earns its place among the most unreliable engines still in production today. Jaguar Land Rover's Ingenium 2.0-liter. Jaguar Land Rover's Ingenium 2.0-liter engine debuted in 2016 as a cornerstone of the company's pivot to in-house powertrain development, breaking ties with Ford's outsourced Duratorque diesels and EcoBoost petrols. Designed from the ground up as a modular platform, the Ingenium family brought together 4-stroke inline 4-cylinder petrol and diesel units with identical 500 cubic centimeter cylinders. At a glance, this engine appeared to embody the future, fuel-efficient, emissions-compliant, and packed with advanced features that could scale across Jaguar and Land Rover's increasingly electrified lineup. Technically, the Ingenium 2.0-liter is a turbocharged inline 4-cylinder engine, available in both petrol and diesel variants. It uses direct injection, with petrol versions employing a 200-bar solenoid injector system and diesel versions operating a high-pressure 1800-bar Bosch common rail setup. Cylinder heads and blocks are aluminum, with integrated exhaust manifolds for improved thermal efficiency. Both versions offer variable valve timing. The valve train operates with 4 valves per cylinder and a double overhead camshaft configuration, while split-circuit cooling and variable oil and water pumps round out the suite of efficiency-enhancing technologies. Power ranges from 148 to 296 horsepower in diesel form and up to 398 horsepower in the hybridized petrol plug-in hybrid variants, with torque spanning from 280 to 472 pound-feet. Ward's Auto named the 247 horsepower petrol Ingenium one of the 10 best engines in 2018, recognizing its smooth delivery and refinement. But behind that early acclaim lies a catalog of mechanical failure. One of the engine's most critical weak points is the timing chain system. In theory, timing chains are meant to last the life of the engine. But in the Ingenium, especially diesel models, these chains often stretch prematurely or snap altogether, leading to catastrophic interference between pistons and valves. At the root of this failure is not just a weak chain, but brittle plastic chain guides. When these guides degrade, they shed particles that clog the oil pickup tube, causing oil starvation. That, in turn, leads to worn bearings, turbocharger failure, and in extreme cases, total engine destruction. Jaguar Land Rover introduced an upgraded chain in 2019, but it did nothing for the thousands of engines built prior. Repair is not cheap, and many engines simply aren't worth saving once the damage is done. Compounding the issue is oil dilution, particularly in diesel Ingenium engines. This occurs when unburned diesel fuel enters the crankcase during the regeneration cycle of the diesel particulate filter. Short trips, stop-and-go traffic, and cold weather prevent full DPF burn-off, forcing the engine to inject more fuel in an attempt to reach necessary temperatures. The excess fuel slips past the piston rings and mixes with engine oil, degrading lubrication and thickening the oil level beyond safe limits. It's a dangerous cocktail that accelerates timing chain wear, damages turbochargers, and undermines critical engine seals. In 2017, JLR acknowledged the problem with service compliance notification, walking back its promise of 21,000-mile service intervals and recommending oil changes be based on driving style. But for many, the damage was already done. Then there's the turbocharger, a high-performance, ceramic-bearing twin-scroll unit that, when it works, delivers excellent response. Unfortunately, it's another consistent point of failure. Fuel injectors are another costly pain point. In diesel models, overfueling injectors can superheat combustion chambers, melting pistons, cracking liners, and killing compression. In 2018, Jaguar Land Rover issued a fuel rail recall in the United States and other markets for certain 2018 model year XE, XF, F-Type, E-Pace, and Discovery Sport vehicles. That same year, another recall was issued for Velar, Evoque, and Discovery Sport vehicles due to software errors in the powertrain control module. The problems don't stop there. A major safety recall in 2023 targeted several 2019 to 2022 models fitted with the plug-in hybrid Ingenium petrol engine, including the Defender, Range Rover Velar, and Sport. In this case, the coolant pump drive belt was prone to damage, which could lead to cooling system failure and overheating. Despite all these technical setbacks, Jaguar Land Rover continued expanding the Ingenium lineup. In 2020, they introduced 48-volt mild hybrid systems and plug-in hybrids, like the P400e, combining the 2.0-liter turbo petrol engine with an electric motor for 398 horsepower and 472 pound-feet of torque. These versions are smoother and more efficient, but still based on the same fragile core. Ultimately, the Ingenium 2.0-liter engine is a textbook case of brilliant design undermined by poor durability. For anyone considering a used Jaguar or Land Rover with this engine, particularly pre-2019, due diligence is not optional. It's a machine that demands constant care, shorter oil intervals, and a close ear for rattles. Because when it fails, it does so in spectacular fashion. The Ford 1.5-liter EcoBoost 3-cylinder. The Ford 1.5-liter EcoBoost 3-cylinder engine made its public debut in 2013, first launching in China within the Ford Mondeo before arriving in North America in the Fusion later that year. Its introduction marked a strategic evolution from larger 4-cylinder and naturally aspirated units like the Sigma 1.6-liter and Duratec 2.5-liter engines. By downsizing to 3 cylinders and leveraging turbocharging, Ford was able to deliver comparable performance while achieving lower emissions and better fuel efficiency, a clear response to tightening global regulations and shifting consumer expectations. Internally codenamed Dragon, this engine evolved from the architecture of the smaller 1.0-liter Fox engine and introduced several notable technologies. Among them, the integrated exhaust manifold cast into the aluminum cylinder head allowed for faster warm-up and reduced turbo lag. It was the first 3-cylinder engine in the world to feature cylinder deactivation, capable of shutting down one cylinder under low load conditions to improve fuel economy by up to 6%. The engine also featured twin-independent variable camshaft timing, TVCT, a water-cooled charge air cooler, and a computer-controlled clutch on the belt-driven water pump to enhance efficiency. With a displacement of 1.5 liters, this turbocharged inline 3-cylinder engine uses direct or combined port and direct fuel injection depending on the model year. It employs 4 valves per cylinder with a dual overhead camshaft setup and aluminum block and head construction. Power output ranges from 148 to 197 horsepower, with torque figures reaching as high as 290 pound-feet in performance applications like the Ford Fiesta ST and Puma ST. In the tuning world, this engine has carved out a modest following. While not a powerhouse by default, its responsive turbo and light architecture give it decent tuning potential, especially in the ST variants. Coolant intrusion stands as the most serious and well-documented issue plaguing this engine. This defect involves engine coolant leaking into the combustion chambers, often caused by cracks in the engine block, thin cylinder walls, or faulty head gaskets. When this occurs, white smoke, rough running, and overheating are early warning signs. This problem has been reported most frequently between 70,000 and 100,000 miles. While Ford issued technical service bulletin to address this issue in earlier 1.5-liter 4-cylinder variants, similar problems have also emerged in the newer 3-cylinder versions used in the Escape and Bronco Sport. Ford claimed updated designs would resolve the problem, but numerous owners remain dissatisfied, leading to a class action lawsuit alleging that the fixes, such as adding coolant sensors, fail to prevent the root cause. Another concern is carbon buildup on the intake valves. While less catastrophic than coolant intrusion, it can still cause rough idling and misfires. Later iterations of the engine addressed this by incorporating port fuel injection to help clean the valves during operation. In more recent years, a new issue emerged: cracked fuel injectors. Some 2022 to 2024 Escape and Bronco Sport models, equipped with the 1.5-liter Dragon engine, were recalled under campaign number 24S16. Ford responded with a multi-step remedy that includes a software update to detect fuel rail pressure drops, a dashboard alert to inform the driver, and a fuel drain tube to redirect leaks away from hot engine components. Altogether, the Ford 1.5-liter EcoBoost 3-cylinder engine embodies the promise and pitfalls of modern powertrain downsizing. It offers strong performance and innovation on paper, but recurring issues, from coolant leaks to cracked fuel injectors, have cast a shadow over its long-term reliability.